Yeah, you can read, right? Yeah, so let's start with transformers. So as you all know, transformers are the new, what do you say, the next, like the most talked about model in town. In machine learning, in AI, everywhere you will be hearing transformers. So I'm a millennial, so I don't know what Gen Z watch nowadays, like K-dramas or something, but we used to grow up with transformers, the cartoon, and you must have seen the movies. So there are three kinds of transformers. Basically, since I think it's an EE course, there will be electrical transformers. Then you have the transformers from Cybertron, and then you have the ML model transformer. So let's go to the prehistoric times. So what is prehistoric? Things before 2017 is what we call prehistoric in ML. So anything like before like 5-6 years is like it's gone. It's age old times. So what happened then and what changed in 2017? So, since you are an intro to ML course, you must have all seen a lot of ML architectures like CNNs, RNNs, LSTMs. And mostly these architectures were used for different things. For example, LSTM and RNNs, these are sequential architectures for handling sequential data like language, translation, next time forecast, like series forecasting, things like that. CNNs are mostly used for vision, like when you have a image classification, video classification, all these problems, you use CNNs. And also, if you are someone who used to do like reinforcement learning, you have a separate kind of architecture. If you have someone who used to do stuff with graphs, you have other architecture. Like for proteins, you have some other architecture. So different like application areas use different kind of architectures. There was no uniformity. So before 2017, so I just like put two papers. So neural machine translation using RNNs because it's a translation task. If you have an image classification, you have a deep convolutional network. So all these fields of ML or the application areas of ML use, since it use different models. The issue was a person from CV could not understand a paper from, for example, NLP, natural language processing. So the amount of communication or the information crossover was very less in those times. Second thing was like it was mentioned in the previous talk, LSTMs, RNNs, all these things had an issue of long range dependency they couldn't capture because you start with a sentence and you keep on feeding more and more data. Let us say you like give an entire book to the model. So it will have forgotten the first page by the time you give the last page. So this issue of long-term dependency is there. And then there is something called scalability. So the common intuition is you make bigger model, you should get an improvement in performance. That is scalability. This was absent in all these models, like all the CNN models, LSTM, RNNs, because they all started peaking after some point, and the extra neurons that you add to the model, the extra parameters, didn't give any improvement. So this is a limitation of LSTM architecture in the context of language translation. For example, in this, as you can see, what LSTM used to do is you give all the input together because you cannot have a translation task where, for example, I say I am a boy, and in Hindi it will be main ladka hu. The problem is you cannot do a word by word translation because I am a boy, the boy comes at the end, but main ladka hu, the ladka is in the middle. So there's an issue there. So you have to feed the entire sentence, input sentence in one go, and then the model has to start predicting the output. So the problem with this is with LSTM, there is something called information bottleneck. You have the stealth state where all the information is contained, and that has to pass through, and then the LSTM will start generating the output. So the amount of information that can be like transferred is limited by that bottleneck. Second is when you look at computer vision tasks. So in computer vision, for example, if you give this image and ask the model, like 6, the number 6 is connected to which other number? So it has to tell 36. But for understanding that, the model needs to be able to see everything together. If you remember the CNN lecture, what CNNs basically have are kernels. And the kernels are actually very small, which is one of the things that gives it the efficiency. Like you have a reduction in parameters because the kernel size is very small. So if you use a 3 by 3 kernel or a 6 by 6 kernel, the kernel size is actually not big enough to capture the entire information of the image. You need a kernel as big as the image, but then it defeats the whole point of using a CNN. And normally, simple tasks like image classification, this is overcome by using deeper layers. The idea is, as you go deeper the layer, you have a sequence of kernels, and the information will be converged, and the model will learn the overall information from the image, which is actually which is actually enough when your task is image classification. Like in the image, what do you see? That is fine. But when your task is much more nuanced, like asking like is 91 connected to 88, then it cannot just get away with telling what is there in the image. It needs to know like the long-term dependency, like how is one part of the image connected to another part. And that is missing in all the architectures. So ELRA is something called a long-range benchmark. It's a benchmark where the long-range dependency detection is tested on ML models. And this is one of the tasks called Pathfinder. The basic task is, so there's a positive sample and negative sample. The positive sample is you have two white dots and a lot of dashed lines. The question is, are the two dots connected by dashed line or not? So the model needs to understand where the two dots are. It also needs to figure out that the dash line is actually connecting it. And that's a very hard task, which none of the models that have been taught till now can solve. So let us come to attention. So what is attention? So when LSTM and RNNs were being developed, it was understood that this particular bottleneck is an issue, that you cannot pass the entire information from the input to the in the cell state. Like there has to be a way. So for example, language translation, like leave of the way while generating the output. If you can look back at the input while generating each of the output word, it will be good. Because then like in some sense we can modify our output based on what are the input words. In a way, it is like attending to the input words when we are generating the output. So this was the model. It was in 2014. This paper came. Neural machine translation by jointly learning to validate and translate. Here, this is what we call attention map, where the input and the output, how each input is attending to each of the output. So as it means the diagonals are almost always like bright, because most of the time this is I think from English to first. Most of the time, like I am a boy, man is a customer. The man will be at the same position in both the thing. But there are people where it is not matching. So that is attending to some other position in the input. Like the third position of the input will get attending to some seventh position of the output to generate that particular thing. And initially it was called as RNN search. In the paper they call this RNN search, where the RNN is actually searching the input and it is trying to rate which particular input is needed to generate that particular output. So I don't know whether you know who is Yoshua Bengio. Yoshua Bengio is one of the leading pioneers of ML, along with Jeffrey Hinton, Jan LeCun, and everyone. And Yoshua Bengio is the one who suggested to use the name attention instead of RNN plus. So because now comes the era of attention, and you will understand why it is important now. So this is the all famous transformer architecture. So this came in 2017, and this changed over. So what is attention? Like what did this paper do that none of the other papers before did? So earlier, like as I told you, in this case, what they did was they used a CNN, used an RNN with an attention kind of a mechanism, which can look back at the input. What this paper told is attention is all you need. You don't need an RNN. You don't need a CNN. We don't need anything. Just stack attention blocks on top of each other. You create a network with only attention layers, and the network will perform well. So this particular paper was actually for the task of machine translation. So I think if you go to like read any ML paper, at least on the current times, they will be referring back to this particular figure or something similar. So what it has is basically an input. In the left side, it is what we call an encoder. In the right side, what we call a decoder. So you give the input sentence to the model, and in the right side, it will start generating the output. And I will explain what an attention mechanism is. So what are the features of this model that actually like gave it a boost over the other things? First thing, it removed all RNNs, LSTMs, everything. Like because it just kept on becoming complex. You had an RNN, which is a simple architecture, and then you made an LSTM, which has like multiple gates and everything, which was then GRU also. GRU also had GRU was a simplification over LSTM, but it also had gates. So how to like, and it was getting more complex. Like if you needed more long range sequences, like if the sequence length is getting more than 1,000 words, 2,000 words, these were failing. So this removes everything. Only attention blocks are there. Second thing was it uses something called positional embedding. So the problem with this model is this doesn't understand the differences in position. I will explain that why when I explain attention, why it doesn't understand that. So you have to feed in the information of position of each word along with the input. So that is something that we do. We give the information of, it's very simple. That is that. So basically, position like for example, I am a boy. You just give the number 1, 2, 3, 4 along with the input. So these words will be converted to vectors. Will be a vector, and then you attach one more vector with the number that is the particular position of that guy. Residual connection. This is something that you might have seen with CNNs or ResNets. So residual connection is basically to ensure that back propagation is so smooth. Like if you have a layer, you give something like this, so that there will be a bypass connection. So the gradient can flow back smoothly. It won't get stuck, and you can get over the issue of vanishing gradient. So basically, in any transformer architecture, basically you will have two major blocks. You will have something called an attention block, and you have an MLP. An MLP is nothing but a multi-layer perceptron, which is basically a simple neural network with a nonlinearity in the middle. So whenever I say MLP is just a multi-layer perceptron, 2 layers, there will be some ReLU or something in between. That's all. And one of the things they changed is they started using layer norms instead of batch norm. Batch norm was very popular, especially in ResNet kind of architectures. They changed to layer norm and showed that it performs better in this kind of model. I will explain what multi-head attention is. And so this is the biggest advantage. So this was in some sense. So I don't know, like there is something called imagine moment for computer vision. So in computer vision, the first time the model actually defeated the human level image classification happened in 2012 when the ResNet, not ResNet, I think AlexNet defeated the human level in image data set. So something similar happened with this particular model because this model could be parallelized. It could run on GPUs. One of the main reasons why CNNs became very popular is because CNNs are parallelizable. You can feed your entire input together and it will do it very fast, parallelize it in GPUs. RNNs, LSTMs cannot be parallelized. You have to feed input one by one. So it's a sequential model. You cannot give all the input together. Even if you give, it will only do it one by one. So this model can actually take the entire input together and it can run on GPUs. So it became like a watershed moment for NLP and especially machine translation. So I don't know how many of you have been using Google Translate before 2017 and after 2017. There is a clear change of quality of the kind of translations that it has. It is because of this. This change from the LSTM RNN models to transformer-based models. again, I don't know how many people have seen like Lord of the Rings, but I hope you get the reference. So again, like I said initially, all these different computer vision like ML programs had separate architecture for that. But once this came, the transform architecture came, it started being used for everything, and we started using state of the art result for all the tasks. There is not a single task where you cannot throw transformer and get good result. So it's like what at this point, like currently in ML, if you have a task, like somehow change the task to the sequence task and just feed the transformer, you are assured to get good result. Just that you need to have compute and data. That's all. So this is the heart of transformer. Like what is this magical operation that is giving this superior performance over everything else? Yeah. So this is called self-attention. And what is self-attention? So self-attention, this is the equation. This is the only equation that you need to know to do this thing. And it is basically, I will explain, I think, more than showing the equation. So basically, it's multiplication of two vectors called Q and K, which is query and key vector. And then you take a softmax over that. So you know what a softmax does? It changes, like it gives an output between 0 and 1. And then you multiply that to a value vector. So basically, this is the weighting of a value vector in some sense. So I will show what exactly it does. So you have an input vector. So this is like, let's say I am telling I am a boy. I will be a vector, I am will be a vector, A will be a vector, boy will be a vector. You follow, right? Now, what attention does is it generates two vectors from each of the inputs. So each of them is called the input token. So we can say input vector, input token interchangeably. So we have four tokens. Each token will generate two vectors from the input. And one is called the query. Each will generate three vectors, not two. It will generate three. So one is called the query vector, one is called the key vector, and one is called the value vector. So this is done by like matrix multiplication. The input vector will be multiplied with a tensor, and it will generate three different ones. There will be three tensors with which it will be multiplied. Now, what happens is, so for each input, this happens. So there will be query key. So I am telling Q1, K1, V1 for the input vector 1. Here's Q2, K2, V2. There will be Q3, K3, V3. So you get the idea. So that is what is shown there. So you have a query, you have a key, you have a value. Now, and here is this is all attention is. You take the query of the first vector, you compare with the values of every other vector. Not value, sorry. With the keys of every other vector. Yeah. Which is basically being shown there. You take the query and then of one input token and compare it with every other key vectors of all the other input tokens. So basically here, this is what we call as the input token 1 is attending to every other input. So it is looking at all the other inputs. So you can understand it as like each of the inputs will be like some vector. Now this vector is looking at all the other vectors and trying to find a similarity. How similar am I to other inputs? So for example, imagine like my name is Pranav. I am a boy. So the next I should know that this I is Pranav. So there should be a way to look back to Pranav for that particular I. And this mechanism allows that. It basically allows every single input to attend to every other input. So now you understand how the long distance dependency can be solved through this. Because every single part of your input is actually looking at everything else and trying to find whether it is important to you. And what it does is, it once it looks, like for example, Q1 is looking at K1, Q1 looks at K1, Q1 looks at K2, Q1 looks at K3. Then what it does is, it does a multiplication. So basically, it's a cosine similarity check. And then this is a dot product. And then you do a softmax. So now what happens? You will get in some sense a weighting. Like, so for example, so in this particular diagram, that softmax is what is called as a score. So you have a query of the input one, looks at the value of input one, and looks at the key of the input one, and it generates a score in the blue. It again does the same thing. The query of input one will be looking at the key of input 2, and it gets a softmax, it will generate 0.5. Similar for input 3 generates a score of 0.5 after softmax. Now comes the multiplication with the value vector. So every input has a value vector. V1, V2, V3, V4, V5. And the result of the softmax, whatever number we get, the softmax will output a number, it will output a vector. This particular number is the weight of that particular input. So now you have weighted sum over all the V's, using the particular softmax output as the weight, which is shown there. So you get like, so this will be 0. That's why it is 0. You take the second one, you get like the value. You take the value of the input 2 and you multiply it with 0.5, you get the multiplication. After multiplication, you get that particular vector. So you get all three outputs. Now you take the sum of it. Vector addition, simple vector addition, and you will get a final vector. And that final vector is the output for input 1. This is just for input 1. So basically what happens is, input 1 looks at every other inputs, like in some sense, it looks at all the information that is important for input 1 from all the other tokens, and then generates the output for input 1. And this happens for all tokens. So now input token 2 will do the same thing. You look at every other thing, you generate output for that. So I think like in some sense the animation for it is computing the attention score, just input 1. So this is like the final output. And this is the whole process. This is generating for input output 1, output 2, output 3. Any questions? Because this is a little bit complex, but if you like look back and go slow, like slowly, it's a very simple process. Okay. So the idea is, for example, Q is query, K is key, and B is value. So value means that in some sense, what should be the what information present in a particular token that should be transmitted to the next slide. Query and key is like is particularly for who is asking what is important and who is giving the information. So query vector. So for example, if query vector is for Q is for input 1, the input 1 vector is asking who are all in the input who is important to me. Like the context, for example, if it is let's say like I give 50 sentences description about me, in which I am telling that I went to a particular school. Now, after like some 10 sentences, there is again a mention of like, oh, the school that I went. It needs to understand that, okay, this is again connecting to that particular word. So when the school is mentioned here, the query of the school vector will try to look where else are things related to school mentioned throughout the thing. And the value vectors of all those words is are important. It will generate the softmax output, the weight of that particular vector, and the value vector of those words will be the final thing that is becoming transmitted to actually generate the final output for the school word. None of these get changed. The moment you feed the input, the query and value are generated. At least in the inference line. By training, your model task is to learn how to generate these three vectors. Yeah. That you want to the next layer. Yeah, like so this thing is repeated again and again and again and again. And it goes on. So like I said, if you look at the equation, like if you compare the equation of this with LSTM, RNN and everything, this is very simple. It's just multiplication. Yeah. Yeah. So for example, if you have an input, input is mostly one-dimensional. Like one-dimensional in the sense like it will be a sequence of vectors. It will be a sequence. And all of these things are similarly vectors. So how do you generate a new vector from an old vector? You multiply it with a tensor. Basically, to generate the key equivalent value. So if I mention the input as x, what you do is you multiply it with a big tensor q to generate your q vector. So it is just an tensor is just a set of parameters. Like so, for example, in CNS, you had a kernel, right? Yeah, and you multiply your input with the kernel to get the output. Yeah, similarly, this is the set of parameters, the learned weights of the model. So actually, when you're training your model on like text or image or everything, what you're actually telling the model is learn this Q matrix to generate a good Q vector. There will be a V matrix which will generate a value of tensor, and there will be a K matrix which will generate a key vector. And these things are, and here the Q and K gets multiplied. It's a dot product. You take the softmax. Actually, there's a sigma, like of all the so basically it's a BI. So this is Q. So basically the actual formula will be Q. Q. The output for the particular token I will be equal to sigma over all J softmax. The Q query for the ith one with key for all the J times V for all J. This is the thing. It's a matrix multiplication basically. It's all it's a vector multiplication basically. It's all vectors, and all these are generated from these tensors. And the task of the training is to learn these tensors based on your text. So here something happens that no other model can do. Your model can change the output based on your input. In other models, once the parameters are fixed, the output is fixed for the particular fixed input. But here that is not the case because there is input dependencies that it is learning. Depending on what your input is, it knows how to give attention rates to different parts of your input on the line. Only thing that the model needs is these three vectors. And in some sense, this is an intuition. We don't know exactly why this architecture works so well, but the intuition is it is learning all the information. For example, ChatGPT. How is ChatGPT so powerful? It is trained on the entire internet. And when it learns the entire internet, in some way, all the information is saved in these three matrices. Because this is like a trillion parameter model. So there are like trillion various parameters in these matrices along all the layers. And that is where all the information is saved. So these are all, yeah. Yeah. Everything is a hyperparameter. The number of layers, what should be the dimension of this. So the bigger your model is, I think for ChatGPT, the input token length itself is something like more than in the range of hundreds of thousands or 1 million input it can handle. And I think the vector size for all these things are like in terms of thousands. The shape of the vector, it will be the embedding and everything. So yeah, it's pretty big. So here is where the scalability comes in. This model, you increase it, you keep on increasing, you add more and more layers, more parameters, the performance keeps on going up. We have still not reached the cutoff yet. You give more data, more parameters, the performance will keep going. Even today, that is the case. We have still not reached okay, this is the beyond this, no matter what you do, the performance, it will stop improving. It is. It is. So, and that is the problem with transformer models. The problem with transformer models is in every input. So if you have any tokens in your input, every token has to look at every other token. So basically the computational complexity is XY, quadratic. But since it is giving us good results, companies are like, who cares? We have money, we will train. So that's why it is so successful, because at this point, nobody cares. At least the people with money don't care. Yeah. So the first dimension architecture we started had an encoder and a decoder. And then later, so this was mainly for one particular task. The paper was only for telling that how to do machine translation. You have this architecture, we can do machine translation well. They did not predict that or did not think that this architecture will become so general. So there are two halves of it. There is an encoder and a decoder. And yeah, it also depends that first we are in providing some input for the second encoder to decoder. Yeah, so that is called cross attention. I think I just skipped that. Yeah, not here also it's not there. That's fully fair. There is some dependency. For this particular task. For this particular, this is the first paper. So this is the first architecture where the architecture of transformer came. So this is not how we use it now. Yeah, that's what I was trying to tell. So, like I said, this is for machine translation. You need to look back every time you need the output. So what happened was, people were like, why do you need an encoder and a decoder? We just need one of them. And that is BERT and GPT. Yeah. So multi-head attention is, so what I told you this is self-attention, which is like every input looking at every other output. If we have this in parallel, so what you arrange like that, every layer there is multiple attention heads. So this is what happens in one attention head. Every input is looking at every other layer. But I can have that same thing parallel. I make copies of the input, like 5 copies of the input, and send it to 5 different ones. And then I concatenate it. Again, I send it next 5 rounds. So that is called multi-head attention. And the idea of doing it is, the intuition is that one attention head will learn one feature. So if you have multiple of them aligned in parallel, you can learn more features from the input in one particular sense. For example, with NLP, maybe one will learn nouns, one will learn verbs, something like that. Nobody knows. So like I said, this came like 6 years back. There is no interpretability on what this model is actually learning or how it is working. So interpretability in machine learning is a different field altogether, and it is still in a SVM phase. Even clearly, we don't know why batch norm works or any of these things work. Like there's no mathematical understanding or like even perfect understanding of any of these things. It just works, and it's an empirical science. Yeah. So if you only use the encoder part, which is just what you say, attention and NLP, which is like the feed forward network. That is called the encoder, and this is what Google uses in most of their tasks. Like, I don't know whether anyone heard BERT. BERT is one of the main models that Google used in the initial language translation times. So BERT is bidirectional encoder. Bidirectional encoder for bidirectional encoder representation using transformers, something like that. So it only has encoder. So that is why you can see it is everything happening to everything else. You have the input and then it is to power. So it's like total attention, everything is happening to everything and you generate the output. GPT uses the decoder thing. Only decoder. They don't need the encoder. So why is it that? So GPT is trained on something called language modeling. Language modeling is predict the next word given all the previous words. So in that case, you cannot actually see the next word. So every time you have to for example the thing is, let's say I have text and that's how you train this model. You have a text, you feed the entire text to the model and let the model learn the dependency. And the task will be, if I will just mark certain issues. Like if I am giving a sentence like I am a boy, I will remove the boy. Or like use like random words in between I will remove and I will ask the model predict the missing words. So this is the pre-training task for these models. This is a self-supervised task. You don't need to actually have the input-output pair. The model can be like easily trained using this task. So the creating data set is very easy for this kind of models. But in GPT, so in BERT, the task is something called master language modeling. Like I randomly take words in between the sentence and ask the model to learn. So the entire model can actually, the input can talk to every other input because it knows like the first word, you might know the last word, the middle word is missing. But in GPT's case, that's not the case. It's always the last word that will be missing. It has to predict the last word. So in those cases, only one direction attention should go. Like this particular word can look at every word before it, but it shouldn't be able to look at every word after it. So that's only a difference in the way GPT and BERT work. So literally there isn't much difference in these two, the way these models are trained or like the performance or anything. It's just that one went with just the encoder and one went with just the decoder. Yeah. And now come to vision transformer. So vision transformer. So now you understand that basically you need a sequence of input tokens. And then everything will happen to it and it will learn everything that you need to know. So how do you do that for an image? Because an image is a two-dimensional thing. How do you do that? But you want to use transformer because transformer is giving super results in NLP. So what to do? Change the image to a sequence. And how do you do that? You basically take the image, you break it, make it patches. Then you take the patches and you make the patches as a sequence, which is what is done here. So the transformer part is playing. That's what it does. So the input is just break it, make the sequence, send it. Now you need position information when you break an image like this. So you just mark every image and all the patches with numbers and just feed it along with it. It looks very stupid, but this like is the state of the art. So this is what it does. It just sends it to the input, adds the position of everybody, sends the encoder, to get out. And this is vision transformer. So now you get the idea. And if you can think of a task where this kind of thing is never used, you can just throw a transformer at it. Just make sure that you make the input as a sequence. So what are the things that can be done with it? You can use it for speech recognition because audio is a sequential thing. You create it, it will work. The second thing, protein structure. I think you might have heard of AlphaFold. Is Google's protein synthesizing model. And then you have, if you have reinforcement, you're doing reinforcement learning, you have this action, state, all like the reward and everything. You just make that as a sequence, like a language with words. Then you can use a transformer on it and it will work. Then another paper came called Alpha Tensor, in which they basically used reinforcement learning with transformers to solve mathematical proofs. So they actually found like solved matrix multiplication in like much less time. Like it found new algorithms actually. And another thing that no other model previously could was handle multimodal input. So you have text, you have image. So you earlier you needed to use like LSTM and CNN, and it is very hard to connect them both. But now you have one model. You can feed whatever kind of input you want. Just that you have to just make the input sequential. So you can handle text, audio, video, everything together. So the era of multimodal input models started coming. Yeah. So coming, like this is the end of my talk. So this is okay. So absolutely, like you have the input, then you pass it through attention module. So into the normalization. Normalizations are just to make sure that that propagation is removed and stuff like that. But we don't know how it works or why it works. And so you have self-attention, you have NLP. So then it became very evident that do we really need self-attention? Like till now, the entire talk I have been telling how amazing self-attention is. It is doing all this long range independent this that okay. But do we really need self-attention? So people, because of this computation of self-attention, people started trying to develop new architectures. Like it's become more efficient, but can still give good performance. And that is when the idea of token mixer came. So token mixer is basically the same architecture, but the self-attention, you have to mix the token mixer. But what is a token mixer? A token mixer is mixing the information from token. Like if there's a token there, there's a token here. You somehow mix the information and feed it to the next layer, which is basically what attention does. Can be more efficient ways to do that. So many different models came. One is called FNet, which is Fourier. Instead of using attention, they use Fourier transform. In another model, instead of using attention, they use Asian NLP. In another, they use data summation. In another, we use behavior transform. So it is the results show that apparently you don't need transforms. Like you don't need attention. If the architecture itself is some kind of like what they call meta solver. In some sense, when you have this two-stage kind of architecture with some token mixer and NLP, you can get good results, especially when it comes to computation tasks. And but since transformers are like you feed in any amount of data, they are giving like such good result. Companies have already invested so much on this model that they don't want to even try something new, because training these models are like takes years. Like even GPT took more than 2 years to train. So once you even find a better model, it is very hard to start training again with the same kind of data. Funny thing, I don't know, like not for GPT-4, but GPT-3, when it came, if you read the GPT-3 paper, they tell that they spent almost like around $300 million to train the model. And while training, they found an error in the training code. But it was already like 70% of the training was over. They couldn't stop it because stopping and again restarting training is not feasible because the money that is already invested. So that's the thing. So these models are like what you say, like especially the transformer. It has become such a, because of the scalability, especially, it has become like it cannot be ignored anymore. Like, so if you have a task which has not been solved, let it be any field in ML or like outside ML, just take a transformer and give the data. I am pretty sure it will give very good result and you can publish or do whatever you want with it. So this is the final slide. This is basically what I like. The prompt was show how transformer architecture is ruling over the other architectures in ML. And this is like a visualization of that by the transformer itself. Yeah, thank you.